A car is initially moving with a constant speed v naught. At time t equals 0, a child runs out into the roadway in front of the car. It takes the driver time big T to react and begin to apply the brakes, during which time the car continues to travel with a constant speed v naught. Once the brakes are applied, the car comes to rest with a braking acceleration of magnitude a. The car travels a total distance big D from time t equals 0 to the instant the car comes to rest. A student analyzing the situation makes the following arguments about how the distance big D depends on the initial speed v naught and the time and the braking distance. The arguments are numbered so you can reference them by number later in your response. First, student's argument says objects will go faster. Objects that go faster will go farther as a result. Therefore, big D increases as v naught increases. Does that sound right? Sounds good to me. Next, the more time an object moves, the farther the object will go. Therefore, big D increases as t increases. Well, what if an object is moving slowly and it's allowed to roll more and more and more and more and more? So that one doesn't really hold up. And acceleration is what gives objects motion, which causes objects to go farther. Therefore, D increases as A increases. Well, if you're traveling with a speed of 0.1 meters per second and you have an acceleration of 0.1 meters per second squared, okay, so you're slowly speeding up. But if you start with a constant velocity of 5 meters per second, with no acceleration, obviously, then you're going to be traveling farther in the same amount of time. So those two don't appear to be true. And just for a note, because we've already read through them, I'm going to make a note here, and I'm going to say, yes, this makes sense. No, there's some problems with those statements. I don't know why we have those statements, but they were given to us, and I've already analyzed them, so I'm going to make a little note about them. Next, it says to derive an equation that expresses the stopping distance, capital D, in terms of v naught, a, and t. Good. We love to see the word derive. When we derive something, that just means we're picking an equation that we already know, and we're going to show the steps to make it make sense. So, to make it make sense for the situation, that is. And you'll see as we go along. So, we have an expression for stopping distance, big D. So we're looking for distance. We have velocity, acceleration, and time. So we know this problem has multiple stages to it. And what are those stages? Well, get my vertical line to change these segments. We know for the first situation, it's moving with a constant speed. And then there's time that it takes to react. So while the car is moving, the driver's brain is thinking, uh-oh, lift your foot up off the gas and hit the brake. Well, how far do we travel during that time? That is what we are going to call the reaction distance. Then we have this distance that we travel while we're braking. So the question is asking for the stopping distance, which is going to be the reaction distance plus the braking distance together. So if we find the reaction distance, then we can add it to the braking distance. And that's what we're going to do here. So the reaction distance, how are we going to find it? Well, we will guess. I keep pressing the wrong button. That's a G. That's a nice looking G. All right, so what do we know about the reaction distance while the driver is driving? We know they're traveling with a constant speed, v naught, and we know it takes the driver a time, capital T, to react. So because capital T is given to us, it says in terms of this, this, and this, we're not going to have little t in our ending equation. So let's go ahead and keep capital T here, and we'll keep our speed as v naught. Now, what don't we know about the reaction distance? Well, we don't know the distance, of course. So what equation can we use that relates V naught, X, and T? That's right. X equals V naught times capital T. So next we would substitute and solve, but there are no numbers here, which is a great thing. That means there's no extra step, there's no calculator error potential, any of that goes away. So next up, we go into the braking distance. What information are we given for braking distance? We know that there is a speed, and if you need to go back and reread the problem, do that. And we know that while braking, there's an acceleration. Again, what don't we know? We don't know the distance that this car will actually travel. Is there an equation that will relate these three? Notice there's no time in this equation, so we're going to use the no time equation. And the final speed, we're coming to a stop, right? Comes to rest. So we know the final speed is 0, so we can use that shortcut. And that shortcut is going to be V naught squared 2AX. We can substitute and solve if we had anything to substitute and solve for. Oh, wait, we do! Sorry. We have to solve for X, right? So we have X equals, and I'll just divide 2A from each side, and we have V naught squared divided by 2A. All right, so we have two X's, which is not great, and secret. So we have two X's, which is not great because they represent two different things, right? So I'm going to write a little subscript here for reaction distance, and then I'm going to have a little subscript here for braking distance because they represent different things. Yes, they are both distances, but we got to keep them separate. All right, so we know that we're looking for the total distance, and that total distance is just our reaction distance plus our braking distance. Well, we know that reaction distance is all of this, so it's V naught times capital T, and then we know XB is all of this junk right here, which is V naught squared all over 2A equals, wait a second, is XT one of the terms that were allowed? No. The total distance that it takes to brake should be given in capital D. So just as one last little check, just make sure all of these variables fit into what the question says. I have the question here for you. It says in terms of capital D, V naught, A, lowercase a, and capital T. So yes, we are good. We have double checked and we can